Hey y'all, it's Mr. Lowry. Welcome back. Today we got this Rationalizing Denominators worksheet, and it's yellow. That's hard to see on the video. When I passed it out, it was yellow. Actually, on the front page, we're not going to rationalize many denominators. That's kind of what we're building towards. We needed to talk about a couple other properties first before we could actually do this thing, which is the name of the worksheet. So the back side is actually where we're going to rationalize our denominators the most, but we need to take a look at the front first. Okay, so on the front, there are two properties that we're going to need, and the first one starts with multiplying radicals. Okay, so there's something called the product property of radicals, and it basically looks like this. When you have two roots and they have the same index number, so this is an m root, and I'm going to multiply it by another m root, we can write this as a single m root. Sorry, make sure that looks visible to you. Okay, m and m. We can write a single m root with the product of a and b together under that one root. Okay. Now this property actually works in both directions, so you could write this backwards or whatever. I think we wrote it the other way in class. But for this assignment, what's going to happen is we're going to have two different roots, but they're going to have the same index. So different radicands, but the same index. And we're going to just multiply the insides. And we're going to simplify as we can do that, or as we go. Okay. So let's look at a couple of these. We'll start with, let's do the evens. I think I gave you the odds answers, so let's do that. So right here, one thing to notice is that these are both root 2. All right, you don't see that 2 there. It's kind of invisible, but that's the default. If we have a different number like 3s and 3s, we know it's a different kind of root, but when you don't see a number there, you can just assume it's a square root or a 2 root. So since these have the same index number, we are going to put the two radicands under the same root, and we're going to multiply them. Okay. This only works with multiplication when we're multiplying roots. It doesn't work the same way with addition. Now you could say that 15 times 10 is 150. It's true, it is, and you could write it as 150 if you want, and that would be correct, but that's actually not going to get us to where we want to go. We want to simplify this as much as possible. So what we're going to do is we're going to actually take this radicand, 15 times 10, and we're going to keep factoring it. We're going to keep breaking it down into pieces. So for 15, I have 3 times 5, and for 10, I have 5 times 2. And the reason why we're doing this is we're looking for powers of 2, because a square root, or a 2 root, is the inverse to squaring something. So like this is 5 squared. So now when we rewrite this, we could write it as the square root of 5 squared times 6, because 3 times 2 is 6. And we can see that this root 2 and this power of 2 are actually going to undo each other. They're inverse operations. And we're just left with the 6 inside. Since there's not like any other pairs, like we have a 5 and a 5, there's not any other squared factors, we just have to leave this. And we don't typically write the 2 in there. So I'm not going to write the 2 in the final answer. So 5 root 6. All right, we can do the same thing with higher powers. So for number 4, we're going to just combine the radicands. Now we got to be careful with that word combine, because there's the English version of combine, just the general version means put together, and then there's the math version of combine, which specifically means add or subtract, as in combine-like terms. So we just got to be careful here. We're actually multiplying, so I'm going to multiply these two factors inside. Let's go ahead and factor these a little bit further. So 25 is 5 times 5. And 15 is 5 times 3. And so you can see now that there's that group of 5 in there, right? 5 times 5 times 5. Okay, so that's going to be 5 to the third. I'm going to rewrite this as the third root of 5 to the third times 3. Okay, so let me get that. All right, so the power of 3 and the root 3 are inverse operations. They undo each other. And so I just get a regular 5. I still have the 3 trapped inside the root, and it's a third root. I don't have a group of 3 3s, I just have 1 3. So only powers of 3 kind of escape the clutches of the root 3. So anything with the power 3 will get out, but everything else will stay in there. All right. In number 6, we have some coefficients. So we have a 6 out in front, and we also have some variables inside. That's okay. Whatever's on the outside of the root is we call a coefficient. It's like multiplying the rest of the root. So this is really just a 6 times 1. We don't have to worry too much about that 6 right now, but later on, whatever comes out of the root is going to have to multiply that 6. So this is actually just 6 times this root. So when we rewrite our root 3, we're going to have a 40n and an 100n inside multiplying each other. So I'm going to do 40 times n times 100 times n. And we're going to keep factoring the 40 and the 10. Now, we're looking for groups of 3, and you can prime factor these. Like, you can prime factor 40 down to like a 2 and a 2 and a 2 and a 5, I think. And same with 100, you can do a 5 and a 5 and a 2. So if you want to prime factor it all the way down, if that's comfortable for you, that's great. If you can find bigger factors that are powers of 3, or that will group into a power of 3, that's good. So what I'm going to do here is I'm going to say, I know 40 is 10 times 4, and I know 100 is 10 times 10. So I have a 10 from here and 2 10s from here. So that's 10 to the third. Okay, I still have that extra 4. So that's 10 times 10. That's 10 times 4. There's the 3 10s, and there's the extra 4. So either way, that's 4,000 altogether. 40 times 100 is 4,000. 10 to the third times 4 is 4,000. So same thing. Okay. I also have the n squared, and let's not forget that this is a third root. So the third root cancels the third power, right? So anything that has a third power is going to kind of jailbreak the third root. So I'm going to get a 6. The 6 is on the outside from the beginning, but now I have a 10 that's coming out as well, and it's going to multiply that 6 that's already out there. Inside the root, I still have a 4, which I could factor to 2 times 2, but there's no groups of 3 there. So I'm just going to leave it as a 4. I could have broken it down into 2 squared, but I just knew that there wasn't another group of 3 in there. And then also n squared, same thing. I need 3 groups of 3 or powers of 3 to get out of the third root, and I don't have one there. So final answer here is going to be 60, 6 times 10, times the cube root of 4n squared. And that's it right there. All right. On 8 through 10, we're now doing a different property, and the property is called the quotient property of radicals. So we do have a quotient property of exponents, and this is similar, but it actually comes from the power of a quotient property of exponents. So let me give you that property here so we can work with it. Okay, when you have 2 radicals or 2 roots dividing each other, the radicands can be different, but if the index number of the root is the same, you can just have one big root that has the ratio of these 2 radicands. In other words, I can just put a over b in one big root m, since these are both root m. Now sometimes we can since it's an equality, we can reverse the sides. It doesn't really matter what direction we're going to go in. In this assignment, we're typically going to go in this direction, but you could just as easily reverse this statement and write it the other way. So if you have a fraction within a root, you can break it up into 2 different roots. If you have 2 roots, you can put them together and make it a single fraction. It's kind of up to you. Now with fractions here, ratios, the numbers on the outside are just going to simplify the same way they always would, using the multiplicative inverses. If anything cancels, you can cancel common factors. So what I would do here in this case is I would keep the 3 and the 4, but then I would make the 12 over 3 into one big root. Okay, and so that's 3 over 4, and 12 over 3 simplifies to 4. So I have 3 over 4 multiplying a root 4. So I've just simplified that fraction 12 over 3 to be a 4. The 3/4 is still there. And I can do the square root of 4. That's actually 2. So really I just have 3 over 4 times 2. And since we're multiplying fractions here, I'm going to put a denominator here. And that's just going to be 6 over 4. Now, since we're multiplying fractions, This only works with multiplication, but if we see common factors diagonally, we can cancel those as well. So before I even multiply, I could say 2 goes into 4 2 times, and 2 goes into 2 1 time. So I have a 3 times a 1 over a 2 times a 1. That's my final answer there. All right, well, that was an odd problem, so I should probably do an even problem since you guys have already, I think, the answers to the odds already. So let's jump in and do number 8. I meant to do number 8, but that's okay. So right here I have a 4 on the bottom. Now, if I want to rewrite this, this could be a 1 over 4, right? And then I'm just going to rewrite the radical. So this is 3 over 27, and that's going to simplify to 1 over 3. Nope, 1 over 9, excuse me. Okay. Now we can because 3 goes into 3 once and 3 goes into 27 9 times. Now we can actually go back, and if we want to think of it this way, we can rewrite it as 2 separate roots, square root of 1 over square root of 9. Right. Well, square root of 1 is 1, and square root of 9 is 3. So this actually is 1 over 4 times 1 over 3. So the fourth and the fourth, but we just simplified the roots now. So we went from 2 roots to 1 root to another 1 root with the fraction simplified back to 2 roots. So we're actually using this property both ways. We're taking 2 roots and putting them together and taking the single root and splitting them up. We're just kind of going back and forth, manipulating this until we get something that's simplified. Okay, so that's 1 over 12. 1 times 1 over 4 times 3. All right. Now with number 10, I'd probably notice those 4s and just cancel those right off the bat. Right, 4 over 4. Those are multiplicative inverses, and you're going to get a 1 there. And then from there, I would probably go write a single root, 6 over 10. Okay, so let's rewrite this guy. Since 3 goes into both of those, excuse me, 2 goes into both of those, I end up with a 3 over 5. And I can, I can rewrite that as 2 roots if we wanted to. Okay, now this is where it gets a little bit tricky because it's not conventional to leave a denominator in, to leave an irrational number in the denominator. So we can simplify this and we get root 3 over root 5. Okay, but we don't want to leave that square root of 5 down there. And we need to do something about that. So the name of this assignment is called Rationalizing Denominators, and that's kind of where we're getting. We actually need both the quotient property of of radicals and the power property of radicals to understand what's happening with the rationalizing the denominator. But the gist of it is that this square root 5 is an irrational number. And by convention, or just an agreed way of doing things, when mathematicians get together and kind of compare notes and decide do something the same way, write things the same way, we need to have no radicals in the denominator. So we're not gonna call it simplified until there's no irrational numbers in the denominator. So what we're gonna do is something kind of sneaky. We're gonna multiply by a form of 1. If we take a fraction and multiply by 1, then we don't change the value of the fraction. That's the identity property. We just got to think about what we need to cancel this. So I need to multiply square root of 5 times something that's going to cancel the square root altogether. And I know if I have square root of 5 squared, that will work. In other words, I need 2 copies of 5 in order to break out of the square root. Kind of going back up here. When I have 2 copies of 5 under the square root, I can bring the 5 out, or I can kind of cancel the root. So down here, we just need another square root of 5. So I'm going to multiply the denominator here by the square root of 5 so that I can have 2 5s. But if I do that on the bottom, I also have to do that on the top. Okay, we got to keep this as a form of 1 here. Otherwise, we're changing the value of the fraction. So on top, we have the square root of 3 times the square root of 5. And that is going to be the square root of 15 using the product property. Okay, on the bottom, we have a square root of 5 times the square root of 5. And there's a couple ways to write this. We could write it as the square root of 25, because 5 times 5 is 25. Or we could also write it as the square root of 5 squared. That'll work as well. But either way, we're going to undo the square here. We're going to, the square, the power 2, and the root 2 are going to cancel each other, and we're going to end up with the square root of 15 over just a regular 5. Okay? So we have changed this now so that the denominator is no longer irrational. It was irrational up here, and now it's rational. We have rationalized that denominator. So that's what that process is called. All right. On number 12, we got a similar scenario. We got an irrational number in the denominator. So when we rationalize denominators, the first thing we want to do is we want to see what factors are in that denominator to begin with. So right now I have a 6 and a 6. That's 36. Now we could factor this further. We could factor this to 2 and 3 and 2 and 3 if we want to do that. It's going to work out kind of the same way either way. But what we need is we need another 6. Or in other words, we need another copy of 2 and another copy of 3. So just to make things, I don't know, just make things super clear and to give you a strategy that's going to work every single time, let's go ahead and factor those down one step further. So I have 2 times 3, that's the first 6. And then I have another 2 times 3, that's the second 6. 6 times 6 is 36. Or another way to look at it is 4 times 9 is 36. So that's what we got. And then I'm going to rearrange that a little bit. So I have a 2 squared, 2 times 2, and I have a 3 squared, 3 times 3. But this cube root undoes powers of 3, not powers of 2. So our goal here is to get rid of the root in the denominator, cancel out the root in the denominator. If I end up with a root on the top, that's okay. And again, this is just a convention. It's just an agreed upon way of writing irrational numbers. We don't put the irrational number on the bottom. What we need is we need an extra 2 and we need an extra 3. Okay? So we have to have a cube root so that the cube root stuff can combine, the radicands there can combine. But we need another 2 and we need another 3. Okay? Now notice that these don't match each other. They're close, but we don't need 2 squared and 3 squared in this one. We only need 1 more 2 and 1 more 3 to make the full set 2 to the third and 3 to the third. Okay? On the top, we need to put the exact same thing. And now we're just going to multiply. These are just 2 fractions we're going to multiply straight across. So I have 6 times the third root of 6. And since this can't simplify, I'm just going to kind of leave it as the third root of 6. 2 times 3 is 6. Okay, but now on the bottom, I have the third root. And now I have all the pieces that I need to break out of this root 3 prison. I have a 2 to the third, because there's 2 2's here, and there's another one here. And I have a 3 to the third because there's 2 3's here and there's another one here. Okay, so that's exactly what I wanted. Like, design this. I mean, we designed this to work out. We decided, we picked the numbers that was going to allow us to have 2 to the third, 3 to the third. So now this third power and this third root are going to cancel for both of these numbers. So I have a 6 times the third root of 6 on the top. And on the bottom, I'm going to have just a regular 2, because the power 3 and the root 3 cancel, and then a regular 3, because the power 3 and the root 3 cancel there. So 6 times the third root of 6 over 6, and now I can just cancel these 6's just using the multiplicative inverse property. Right, I have a 6 divided by 6, or a 6 over 6, so those would cancel, and then I just get third root of 6. So that's, again, called rationalizing the denominator. This and this are actually equivalent. They're the same number. We're not changing the value. We're just changing what it looks like. and we can be sure that we didn't change the value, because this whole thing right here is just a gigantic, ugly 1. It's just a form of 1 because we have the same thing on top and bottom. We're just using the identity property here. So that's kind of what's going on with those. So on the back side, we have similar ideas, but we now have variables and we have other higher roots and things like that. So some of these aren't too bad. Some of these take a little bit longer. Let's go ahead and take a look at some of these. Okay. Now, we talked about a property just a minute ago that will allow us to like combine the two radicands here when we have a square root over a square root. So what I would recommend is, before you try to rationalize the denominator, you simplify as much as possible. Okay. So for example, if I wanted to, I could multiply this fraction by the square root of 21n over the square root of 21n to get, you know, the roots to cancel. But that's actually a lot more stuff than I need, because this n will cancel out with one of these n's, and there's a 7 in here that cancels out with one of these 7's, and there's even some stuff that simplifies out here. So before you go rationalizing the denominator, do that as like your last step, or do that towards the end of the problem. What you want to do is you want to simplify as much as possible first. So let's kind of take a look at this. 10 over 2, we can simplify that to 5 over 1. Okay, I'm going to kind of break this fraction up, look at it two different ways. So now we have the root, okay, and I have 70n to the third over 21n. And now we can cancel some stuff. So 7 goes into 70 and it goes into 21. 7 goes into 70 10 times, and it goes into 21 3 times. We also got an n to the third over an n to the 1. So if we use the quotient property and subtract the exponents, we get n squared. So that's kind of what we got there. Now I'm just going to put it back into two different radicals. So I have 5 times the square root of 10n squared, and then I have 1 times the square root of 3, or just the square root of 3. All right, so now we need to rationalize the denominator. We've simplified first, but now we need to rationalize the denominator. We're not fully simplified until we've rationalized all those denominators. Okay. All right, sorry about the bell interrupting there. Okay, so what we need to think about is what else do we need in this root so that the root can cancel. Now remember, this is a second root, or a 2 root, and so we need powers of 2. So I already have 1 3. If I bring in another 3, then I'll have 3 squared, and then I can cancel the root. So I'm going to rewrite over here. 5 times the square root of 10n squared over the square root of 3. And I don't want to change the value of this fraction. So I have to multiply by a form of 1. So if I multiply by square root on the bottom, square root 3 on the bottom, excuse me, which will help me cancel the square roots, I also have to do it on the top so that we keep this full fraction equal to 1. Okay, on the top, we got a regular 5, okay, and when I multiply these two square roots, I can bring the 3 inside to multiply this guy. So I have a 3 times a 10n squared. That's going to give me a 30n squared. Now, I don't have any extra pieces. I don't have to worry about simplifying the numerator right now, because even when I bring this 3 in, I'm not going to have 3 copies of anything. But on the bottom, I'm not going to have 2 copies of anything. But on the bottom, I'm going to have 2 copies of 3. Actually, let me backtrack just for a second. I just misspoke. So notice I have an n squared, and this is a square root. So in the next step, let's take care of that. We'll do it at the same time as the bottom. We could have taken care of that earlier, but that's okay. So now on the bottom, we have a square root of 3 times 3, or 3 squared. Okay. So now the roots are going to cancel anything that has a power of 2, because this is a 2 root. So I got a 5. Okay. Now, since I have an n squared, there's going to be an n on the outside. There's no perfect squares that go into 30. In other words, 30 is a 3, a 5, and a 2, and there's not 2 of anything in there, so I'm just still going to have that square root of 30. On the bottom, the square and the square root are going to undo each other, and I'm just going to have a 3. If there were anything outside of the square root that had a 3 in it, I could cancel the 3, but there's not. There's a 3 inside this 30, but the 30 is kind of trapped inside that square root, so I can't cancel 3 here either. So we're going to go with that guy. That's our final answer, as much as we can do. All right, let's take a look at 16. Okay, this one's going to be a little simpler because we don't have to simplify first. Everything's already simplified as much as possible. The only thing we have to do here really is to rationalize the denominator. So here I have a 5 and an x. It's kind of already factored. So you got to think to yourself, what is going to cancel with our third root? We have to have powers of 3. Right now we only have one 5, and so we need 2 more. And we only have one x, so we need 2 more. We also have to make sure that this is all inside a root 3. And then we have to make sure we do the same thing on the top, so that we're actually multiplying by a form of 1, and we're not changing the value of the original expression. Okay, so on top, we got the cube root. And I'm going to write this out this time, just to see that there's no double factors. I got a 9 on the outside. This isn't in a radical, so 5 squared x squared. Okay, I have no powers of 3 that can cancel with the top root 3. But on the bottom, I've just kind of we've made this decision that's going to allow me to have 3 copies of things in the bottom. I started out with 1, 5, and now I have 2 more, and they're all getting multiplied, so 5 to the third. I started out with an x here, and I have 2 more x's, so I have x to the power of 3. Right? So from here, we're going to simplify this guy. So I have 9. This is going to be 25x squared. We'll just do the 5 times 5 because nothing's going to simplify. But on the bottom, we're going to have the root 3 canceling with the power 3. That's a regular 5. And then the root 3, again, canceling with this power of 3, so that's a regular x. And it looks like we're done here. There's no common factors with 5x and 9. If there was, we could simplify there. We can't cancel the 5 with this with the 5 that's in this 25 because this guy's kind of trapped in the square root and can't pull it out. So we're going to stop there. All right, number 18. Okay, so there's a couple ways we can do this. We can factor that 10 down, which we should probably do just as a matter of practice. You might notice though that 10, when you factor it, that doesn't have any it doesn't have any doubles. It's just a 5 and a 2. So if you wanted to, you could multiply this by the cube root of 10 squared, because we need 2 more 10s, and another m to the 1, and then I'll do that on the top and the bottom. So that's, definitely an option here. This is going to end up being the same thing, but it's probably a good habit to get into, to start factoring first, just so you can double check and make sure you've covered all of your bases. So this is a 5 times a 2 times an m times an m. And what I need is groups of 3 to jailbreak out of that root 3. I need powers of 3 because those are inverses, power of 3 and root 3. So I have 2 m's. I just need another m. That will make 3 m's. I need 2 more 5s, and then I need 2 more 2's as well. So when I multiply here, I'm going to need a 5 squared, 2 more copies of 5. I'm going to need a 2 squared, 2 more copies of 2, and I'm going to need 1 more copy of m. Now this is actually the same as what I wrote before, where I was like, you just need 2 more copies of 10. You can do it either way. This is a little bit more writing, but it's, I think, maybe a little bit safer, just so you don't miss any factors. Okay, now notice that the top and the bottom are identical. They have to match in order for this to actually be equal to 1. Because we can't just take this original problem and just randomly multiply it by some other number. It has to be a 1. But these two guys don't have to match. They look kind of similar, but they're not identical. Because this one has 1 5 and this one has 2 5s. And this one has a 2 and this one has 2 2s. And this one has 2 m's and this has an m. So they don't match, but they are going to complement each other in the sense that when we put them together, we are going to have powers of 3. So on the top, we have a 10 times the cube root. Now, this stuff, notice there's no extra copies. There's no copies of 3 of anything. So I'm just going to turn this into a 4 times a 25. That's just 100. I can't, 100 is a perfect square, but it's not a perfect cube. And I also have an m in there. So that's what's happening along the top. Now also, some people are like, oh, let's just put the 10 in there. I can't put the 10 in there because this is not in a root 3 either. So that's as simple as the top's going to get, unless we have something canceling with the 10, which we might. Okay, on the bottom, I have all these powers now. I have 1, 2, 3 copies of 5. I have 1, 2, 3 copies of 2. And I have 1, 2, 3 copies of m, which is actually exactly what we wanted to have happen. We wanted to have powers of 3 to undo this third power. That's the whole process of trying to figure out what needs to go here to give you powers of 3. Okay, so I'm rewriting the top. And on the bottom, I'm going to have a regular 5, because the power 3 and the root 3 undo each other. I'm going to have a regular 2, because the power 3 and the root 3 undo each other. Those are getting multiplied. And then I have a regular m. Again, the power 3 and the root 3 undo each other. All right, now if there's any common factors outside of the radicals, I can do that now. And since 5 and 2 go into, both go into 10, or 5 times 2 is 10, we're going to get that simplifying. And so final answer, third root of 100m all over m. Okay, so we simplified. We made sure that there was no radical in the denominator. This was irrational to begin with. It's now rational. We have rationalized the denominator. All right. Next up, we got a power of, a root 4. Okay, so this could be kind of fun. What we need to get out of the root 4 is we need powers of 4. And this is already pretty factored. We got a 5 and an x and an x. If you wanted to write that out, you can. But just by looking at it, I know that I need 3 more copies of 5, and that I need 2 more copies of x, because I need groups of 4. So I'm going to do 4th root, and then I'm going to have 5 to the 3, so I have 4 total. And then I'm going to have x to the 2. Again, I want 4 total. So these don't match, and that's okay. They both have a 4th root. That's true. They both have 5s and x's, but this one has 1 5, or 5 to the 1, and this one has 3 5s, or 5 to the 3rd, because we're multiplying. And we have an x squared and an x squared. Those match, but again, we're just trying to get to 4, to powers of 4. All right, on the top, we have 5 to the 3rd x squared. So the top and the bottom of this have to match, again, because this whole thing has to be equal to 1. Otherwise, we're multiplying the original problem by some number besides 1 and messing everything up. But in this case, we're multiplying by 1, and so we're good. We're going to get an equivalent fraction. All right, on the top, we got 5 to the 4th power. Now this stuff right here, 5 to the 3rd, I can just go ahead and turn that into a number because I know I'm not going to have any extra 5s to bring out. So if this was a power of 4, definitely, but it's just power of 3. So that's 5 times 5 times 5, or 125, and then x squared. On the bottom, so that's this guy times this guy. On the bottom, when I put these two guys together, I'm going to have a 4th root, which is great. But I'm going to have a 5 to the 4th, which is what I wanted, an x to the 4th, which is what I wanted. And now the powers of 4 will cancel with the root 4. Top's going to stay the same. On the bottom, I have a regular 5 and a regular x. So now that we have that all straightened out, the numbers outside the radicals can just cancel like a regular fraction. And that's our final answer there. 4th root of 125x squared all over x. All right. Last one, we'll do 22. All right, so we got a square root, just a regular old square root. Now, in this case, I would actually probably try to simplify first because there's a n squared inside of a square root, so let's take care of that. There's also n cubes over n, so there's actually several different ways we could do this, several ways we could simplify this. One of the ways to do it would be to put the 1 over 5 multiplying a giant root 2n to the third over 3n squared. So we could, kind of do it that way, and we could cancel these two n's with one of these n's. That's, I think, what I'm going to do here. So 3 minus 2 is 1, so I got n to the 1 power up here. And now let's put it back into two different roots. So on the top, I have 1 times root 2n. On the bottom, I have 5 times root 3. So that actually kind of makes my life a little easier because now I don't have to multiply by as many things to clear that denominator. There's other ways to simplify this because you actually could have said like, oh, well, the square root of n squared is just n. And so another way to do this would have been to just simplify the roots. So like on top, I have a square root of n to the third. So that's going to give me n times 2n. Since there's 2 copies of n and this is a square root, I can bring out an n. And then on the bottom, I could bring out another n here. And then I could cancel those 2 n's. So either way, you get to here. Whether you want to like combine those 2 radicals into a single radical and use the fraction idea, or whether you just want to simplify each root individually and say, oh, are there any powers of 2 in here that can come out? Yeah, there's like an n squared in there, and there's an n squared in there that can come out. Either way, you're going to get down to this piece right here. So that's pretty simplified, but the problem is we have an irrational number in the denominator, and we don't want that. So our last step is to clear the denominator of any radicals. So this is a square root. I need 2 copies of things to clear, and I want to make sure I'm multiplying by a form of 1. So on top, I have square roots, and I have 2n times 3. That'll be a 6n. On the bottom, I have 5 times the square root of 3 squared. Now I have 2 3's, and so that that power of 2 and that root 2 are going to cancel. So I got the square root of 6n over 5 times just a regular 3 when this 2 and this 3 cancel. And I'm just going to do 5 times 3 right at 15 there. Okay, so we can't really cancel anything else out, and looks like we're good on there. So when you are doing these types of problems on the back here, I would highly recommend that you simplify as much as possible first. If there's anything you can take out, do that first. If there's anything you can cancel, do that first. That's going to make the rationalizing part much easier. Now I think for these odds, they look pretty simplified. Here I would cancel a 3 with the 3 that goes in 6. That's going to help you out a little bit. This is already simplified as possible. This is already as simplified as possible. You still obviously need to rationalize, but there's nothing that can simplify before that. This same thing. But on 21 here, I would probably put the 21 and the 6 under the same root because you can cancel there's like a 3 in 21 and a 3 in 6 that you can cancel. You can also cancel this m with one of the m's in here. So you could combine these 2 roots into a single root, 21m over 6m to the third, and have a big square root over it. You can also look at this and be like, oh, well, there's a power of 2 inside that power of 3. And if you take the square root of a power of 2, like you can get an m coming out here and an m left over. So most of these odds on this page, you don't have to simplify first. It looks like 21, I would definitely simplify some of that stuff first before rationalizing. And also on 13, there's a common factor there you can take out, but mostly already kind of simplified there. You just need to rationalize the denominators. And yeah, same thing over here on the front page. If there's anything that can simplify, do that. So put a 3 over a 6. That's 1 over 2. And you can kind of go from there. So those are all the evens for you. Hopefully that will help you. On the odds, you got the answers, so you can check your work that way. You definitely need to show some work here. There's lots of work that I showed. You can use this kind of as an example of what it looks like to show your work. And just make sure you're showing me some steps. You don't have to show every single step in crazy detail, but I definitely should see a thought process here. All right, thanks guys.